sorry, will be, yeah, minus P L minus X. So this is equal to Px minus by PL. Okay. So now we have our equation now. So going back to our table, so V as a function of X is equal to P. Right. So on our shear force, this will go back up. Right. So this will go back up to be a P. Right. So this will be a P. Right. And then horizontally, right, because it's constant, yes or no? Right. It's a constant. And then the next one, where you have M as a function of X. So this will be equal to, what was it? Will be equal to Px minus PL. So Px minus PL, right? So it's going to be a positive slope. So we know that it's going to be a positive slope, right? So we want to find what will happen when x is equal to L. When x is equal to L, the whole term will be equal to 0. So from here, we know that this is our shear force diagram, right? So over here, this function over here is what? Is equal to mx is equal to PL or Px minus by PL. Okay, so it's positive slope. Over here it's positive slope. When x equal to L, the whole thing is equal to 0. This way it ends up here. Okay, so we have that. All right, and then finally, the last point. Anyone, any question? It's okay so far, right? And finally, when at point D, right, where x is equal to L. Okay, again, now it's a very small strip like this. So you have a load P down here. So over here you have V at point, hold on. So you have a distance. Your datum is still on your left hand side. Now your distance from here to here is fixed at L. Okay, positive shear V at point D, moment at point D. Okay, so again, positive is going up. Right, so this is going to minus P plus by V at point D is equal to 0. So V at point D is equal to P. Okay, and then you summation your moment in the Z direction at point D. Okay, so this is where our point D is. So it's equal to 0. So you have P multiplied by the distance will be 0, right? And then this will be plus by M at point D is equal to 0. So M at point D, the whole thing is equal to 0. So what we have over here is we have V at point D is equal to P, okay? And then moment at point D is equal to 0, okay? So what you see, so all the shear force diagram have to close, okay? So there you go. So this is how our shear force and bending moment diagram is drawn, and now you have formed also your shear force and bending moment equation. Okay, so with all these equations, you will know the trend of how P will affect W or omega, or how P and omega will affect your bending moment. Okay, or how your structure will deform. Okay, now I want to go further. Okay, I'm going to talk more about your shear force and bending moment diagram. I hope I can copy the whole thing. Okay, so I'm going to use right. Okay. So what can you see from here? Anyone? What is the relationship between? So I'm going to ask you guys this now. Okay. So we have different type of loading, right? So let's look at the loading. Okay, let's look at the loading now. Okay, let's look. So can anyone tell me when it's point load, what will happen to the shear force and bending moment diagram? Anyone? Right?
It's a flat line and then a slope for
Okay,
bending moment.
well done. So on point load, right? On point load, the shear force. So shear force I'm going to SF will have 0 gradient. So no slope. Okay. However, for point load, okay, so for point load again, the bending moment which I call BM will have a gradient. Okay, how about distributed load? Can anyone tell me about distributed load?
It's two similar triangles and
No, you don't
happy
call
face.
it similar triangle. Okay, so on distributed load, right? The shear force, SF means shear force, right? Will have gradient. Right, and the bending moment will be a curve. Okay, not a straight line. Okay, non-straight line. Okay.
Hey, Gene,
Yes.
would it always be a parabola or could it be different, curved in a different way?
It will always either be a smiling face or a sad face.
Okay.
Okay. What else can you all see between the shear force and bending moment diagram? Come on, some of you have knowledge with this. What else can you see?
Shear always goes to 0 at the ends.
Shear always go to 0 at the end. Okay. What else?
Bending moment always goes to 0 at the end.
Bending moment 0. Not always. Okay. Sometimes. What else? You cheeky sod. What else can you all see?
It's symmetrical.
It's symmetrical. For this case it is, but that's not always unique. What else? So there's this thing you can see. Okay. I want you to focus from 0 to A. From 0 to A, the magnitude is what? So from 0 to A, the magnitude is what? Negative. Yes or no? From 0 to A, the slope is what?
Negative.
Well done. Now let's look at the other plane. Okay. So there's a center point. If I'm going to draw a center line or a straight line from top to bottom. Okay. I'm not So, okay, my diagram's a bit off. Okay, but let's watch over here. From A to at a certain point over here, which is L/2, right? Your slope now, your magnitude is what? Positive, yes or no? Right? And if you look at your slope, it's also what? Positive. From L/2 to L minus A, the magnitude over here is what? Negative. The slope now, right, from L/2 to L minus A, right, it becomes what? Negative. And then from L minus A to L, the shear force is what? Positive. The slope now is what? Positive. Can you all see that? Right? So there's one more way to check. So the relationship now is this, right?
Eugene, I think you are unmuted.
Eugene, you muted yourself.
Can you hear me now?
Yeah.
Yep.
How long was I muted for?
15 seconds maybe.
15 seconds.
Yeah.
50 seconds. 50.
No,
1-5.
1-5.
Okay, okay, thank you. So the magnitude of the shear force correspond to the what? So the magnitude of the shear force, right, correspond to the slope of the bending moment. So i.e. what you can see down here, negative magnitude, negative slope. Positive magnitude, positive slope. Negative magnitude, negative slope. Positive magnitude, positive slope. Can you see that? Yes? Okay. Now, someone unmute yourself. Can you mute yourself, please? Thank you so much. Okay. So now, from here, where am I going to go? Okay. So what else can you observe? Anyone? What else can you observe?
The magnitude of the shear affects the slope of the bending moment.
So yeah, you're partly right. Okay, you're partly right. So the thing is this. Okay. The thing is this. Hey, where am I now? Oh. Gee, everything just disappeared. So now, the thing now is this. Okay. When the shear force is equal to 0, okay, there is a possibility that bending moment is at its maximum. Right? Why do I use the word possibility? Okay, as you can see from here, okay, as you can see from here, the shear force crosses at A, right, where shear force is equal to 0, and it crosses at L/2, and it crosses at L minus what? L minus A, right? So where at A, the bending moment is equal to what? Minus P over A. Minus P over A. And then for this case, the maximum bending moment is at L/2, right? Now, there's a possibility that the bending moment at point A is higher. Yes or no? It all depends on your distributed load. Like for example, if you look at condition